AP Physics 1 2016 free response. Question number 2. A new kind of toy ball is advertised to bounce perfectly elastically off hard surfaces. A student suspects, however, that no collision can be perfectly elastic. The student hypothesizes that the collisions are very close to being perfectly elastic for low-speed collisions, but that they deviate more and more from being perfectly elastic as the collision speed increases. Part A. Design an experiment to test the student's hypothesis about collisions of the ball with a hard surface. The student has equipment that would be usually found in a school physics laboratory. So we want an experiment to test if a bounce is elastic or not at low speed and high speed collisions. So we want something that would have a ball bounce off a wall. So we can either have a ball ram against a wall, or we can simply just drop the ball. So since dropping the ball sounds easier, let's go with that. So our experiment will focus on dropping a ball from a certain height, and then we'll see how far the ball bounces back up. Now, if the ball bounces back up to the same height, that must mean that energy was conserved and no energy was lost. But if the ball doesn't bounce as high, that means some energy was lost, meaning the collision wasn't perfectly elastic. This experiment would be a good way to test our student's hypothesis on whether or not a collision will be elastic. So, as said earlier, we would want the drop height and the bounce height, and we'll compare these two to see if energy was conserved to determine if the collision was elastic or not. And to measure the height, all we need is a meter stick. Now we have to describe the procedure to be used to test the student's hypothesis. Give enough details so that another student can replicate the experiment. As I said earlier, first drop the ball from a height of 1 meter measured by the meter stick. Then we will record how high the ball bounces through the meter stick as well. Now we can repeat this 5 times and average the values to ensure accuracy, and then repeat at a variety of heights, which I included a few examples here, so we can compare the low height collisions and the high height collisions. Now part B. Describe how you would represent the data in a graph or table. Explain how that representation would be used to determine whether the data are consistent with the student's hypothesis. So since we're comparing the height, we can use a graph. We can make a graph with the x-axis being the drop height and the y-axis being the bounce height. We can plot the data points at each height. And if the graph has a linear slope with a slope of 1, meaning there's a 1-to-1 ratio between the drop height and the bounce height, then the collision would be elastic, as that means the initial height and the final height are the same. So energy is conserved, meaning the collision was perfectly elastic. So due to conservation of energy, the higher drop heights will have a higher collision speed. So to test the hypothesis, we should compare the slope of the low drops and the slope of the high drops. The high drop should have a smaller slope than the low drops if the student is indeed correct. And this portion right here is since the slope is the ratio between the bounce height and the drop height. So since we predict that the high drop is not perfectly elastic, that means some energy will be lost. So the bounce height will be lower than the drop height, meaning if we form a fraction between the two, or we make the slope, then the slope is less than 1. So that's why the higher drops should have a smaller slope than the low drops, if the student is correct. So to summarize, we would basically have a graph, the x-axis being the drop height and the y-axis being the bounce height. And then we'll look at the slopes to compare the ratios between the lower drop heights and the higher drop heights. Even though we're looking at low speed, due to conservation of energy, low drop heights will be low speed collisions, and high drop heights would be high speed. Now for part C. A student carries out the experiment and analysis describes parts A and B. The student immediately concludes that something went wrong in the experiment because the graph or table shows behavior that is elastic for low speed collisions, but it appears to violate a basic physics principle for high speed collisions. Give an example of a graph or table that indicates nearly elastic behavior for low speed collisions, but appears to violate a basic physics principle for high speed collisions. Since we had a graph in part B, let's stick with our graph. We want nearly elastic behavior for low-speed collisions. In other words, we have a one-to-one ratio between our drop height and our bounce height. So the one-to-one ratio means we'll have a slope of 1. That's what this line would depict. Now for high-speed collisions, we violate a basic physics principle. Now there can be many options, but the one I chose to do would be to violate the conservation of energy, since our experiment revolves around following the principles of the conservation of energy. So if we don't follow the conservation of energy, then our final energy would be greater than our initial energy. So when we form our ratio, our bounce height would be greater than our drop height. So this greater y value over the x value means the slope is greater than 1. That's why for high heights, we draw an increased slope, such as this. Second part of part C. State one physics principle that appears to be violated in the graph or table given in part CI. Several physics principles might appear to be violated, but you only need to identify one. Briefly explain what aspect of the graph or table indicates that the physics principle is violated and why. As I said earlier, we violated the conservation of energy. At higher drops, our slope is greater than 1, meaning the bounce height is greater than the drop height. This violates the principle of the conservation of energy, which indicates that the maximum bounce height be the original drop height. Since our slope is greater than 1, the final energy exceeds the initial energy and thus contradicts the conservation of energy. So that would be it for part C and the rest of the second question on the 2016 free response.